Hey everyone, we're Team 20 and today we're going to be presenting on the enzyme acetylcholinesterase. Our goal was to answer the question, how does acetylcholinesterase regulate the acetylcholine signaling pathway? First, we would like to give a little background on the acetylcholinesterase and the acetylcholine molecular structures. Acetylcholine is a neurotransmitter that plays an important role in both the sympathetic and the parasympathetic nervous systems. Acetylcholinesterase is an enzyme that catalyzes the breakdown of acetylcholine through a hydrolysis reaction. This functions to prevent buildup of acetylcholine signal and to determine the acetylcholine signaling. Acetylcholinesterase's active site is composed of two parts, an anionic site and an esteric site. There are also several peripheral anionic sites that can be bound to and lead to non-competitive inhibition. The nitrogen is electrostatically attracted to tryptophan 84 in the anionic site, while the ketone binds to catalytic triad of serine 200, histidine 440, and glutamate 327.
Acetylcholinesterase catalyzes a hydrolysis reaction, severing the ester in acetylcholine, resulting in the formation of acetic acid and choline. When the bond is hydrolyzed, the anionic site first releases the choline, then the acetic acid is released shortly after. This reaction takes only microseconds when uninhibited. Acetylcholine is synthesized by choline acetyltransferase, which combines choline with acetyl-CoA. After acetylcholine hydrolysis, the acetate is converted to acetyl-CoA by acetyl-CoA synthetase with the help of ATP. Here are some means of regulation for acetylcholinesterase.
When it comes to inhibition of acetylcholinesterase, there are two types of inhibitors, irreversible and reversible inhibitors. On the left are pharmaceutical drugs such as donepezil, rivastigmine, and galantamine, and these are all reversible inhibitors. And these work by competitively and non-competitively binding to the acetylcholinesterase. On the right is an organophosphorus compound, and this is a type of irreversible inhibitor. These work by binding to the active site and phosphorylating the enzyme, and this leaves it unable to bind and catalyze acetylcholine. Dephosphorylation of acetylcholinesterase is a slow process and can take up to days, and these can be found in pesticides and nerve agents. Prolonged phosphorylation can cause serious health issues like type 2 respiratory failure and muscular atrophy. On the picture to the right, you can see the different receptors that acetylcholine affects, like the muscarinic and nicotinic receptor, which affect the skeletal and cardiac muscle system. So over-inhibition of acetylcholinesterase can lead to overstimulation of these receptors. Over-inhibition of acetylcholinesterase can also lead to anti-Alzheimer's disease effects. By delaying the breakdown of acetylcholine, you allow for a stronger signal. It also leads to something called sludge syndrome, which stands for salivation, lacrimation, urination, diarrhea, gastrointestinal, and emesis.
An example of modern research of acetylcholinesterase inhibition can be found in the following named paper. In this paper, the purpose was to test the inhibitory effects of natural phenolic compounds on acetylcholinesterase, which is a key enzyme associated with the onset of Alzheimer's disease. This was achieved by using 14 different xanthohumol, naringenin, and acylfluoroglucanol derivatives to test the inhibitory effects on the active site amino acids of acetylcholinesterase. The results showed that 3-hydroxy-xanthohumol and xanthohumol were found to have the greatest inhibitory effect on acetylcholinesterase. There was roughly 72% and 56% inhibition percentages, respectively, between the two. Studies like this one further our understanding on possible ways to inhibit acetylcholinesterase overactivity and delay the progression of Alzheimer's disease.